Hey everyone, in this video we would like to discuss how to design the lightning protection system. What is a lightning protection system? This one, or the lightning protection system, is used to protect the building, for example, against lightning strikes. Okay, so if we have a building like this one and we would like to protect it against the lightning strikes, so what we are going to do, we are going to provide an air termination system or air terminal system. This one is used to capture the lightning strike. Okay, and instead of the lightning strike hitting the building itself, it will hit this air terminal system, such as one rod, or it can be a mesh system, or it can be a group of rods, not only one, but a group of rods. Anyway, a system which is called the air termination system, used to capture the lightning. Now the lightning captured by the air termination system will provide the strike through a wire, okay, which is called the down conductor, which is a high voltage shielded cable used to take the lightning strike from the air termination system to the earthing system. Okay, now you will find that we have here a small device called the lightning strike recorder. This one is used to record the number of strikes hitting the building. Okay, so number one, we have the lightning rod, or the air terminal or air termination system. It is used to capture or pick up the lightning strike hitting the building. Number two, the down conductor or copper strip, which is used to carry the lightning strike from, of course, the air terminal to the earthing system. Number three, the lightning strike recorder, which is this one, used to record the number of lightning events occurring in our system. Number four, the earthing system, in order to dissipate the lightning strike into the ground. Okay, so now we know that we have the air termination system, the down conductor, and finally the earthing system. The earthing system is discussed in other video using the ETAB program, how to design the earthing system using ETAB, and we discussed it using manual calculations. Okay, now what we are going to learn is that we need to learn about the air termination system and the down conductor. So what is the steps here? How to design the lightning protection system? Number one, we need to do a risk assessment calculation. This one, it is used to define the lightning protection system class. Okay, it is class 1, 2, 3, and 4. There are 4 classes. Okay, so we do the first step, which is risk assessment calculation, in order to identify the lightning protection system class. Number two, then according to the class which we obtained, we can design our air termination system. Then we can design the down conductor and of course the earth termination system, which is discussed in other videos on our channel. So how to do the risk assessment calculation? So first we have a group of factors and their definition, which is important for us. Number one, we have a factor called ND. What does this representing? This representing the expected yearly lightning strike frequency to the structure itself we are protecting. What does this mean? This means that how many strikes we expect hitting the structure per year. The expected number of strikes or lightning strikes to the structure per year. Second one, NC, which is the tolerable lightning strike frequency to the structure. What does this represent? This representing the allowable number of lightning strikes hitting our building. So this one, the expected number of lightning strikes hitting our structure in 1 year. NC, the allowable number of lightning strikes to hit our structure per year. This is the allowed number and this is the expected number. If the expected number of strikes greater than NC or the allowable number of strikes, then of course we need a lightning protection system. But if the number of expected strikes less than the allowable number of strikes, then we don't need a lightning protection system. Okay, so the question is we need ND and we need NC. Okay, so this was the thing which we would like to do, or the thing which we are going to do. Now we have another factor called NG, which representing the average flash density in the region per year. Number of strikes hitting each kilometer square per year, or per unit area per year. The number of strikes per unit area per year. And the EE, which is called the equivalent collective area of the structure in kilometer square. This we are going to, of course, know their equations. We have also C1, C2, C3, C4, C5, environmental coefficient, structure coefficient, structure contents coefficient, structure occupancy coefficient, and lightning consequence coefficient. Okay, all of these factors we will see in the next slides. So the first one is called the ND, or the expected lightning frequency calculation. How many strikes we expect to hit our building. This will be equal to ND is equal to NG, which is the average flash density, multiplied by the collective area, multiplied by C1, multiplied by 10 to the power negative 6. Okay. So the first element is C1. C1, this one, which is the structure coefficient, as I remember, environmental coefficient. Okay. Environmental coefficient, what does this represent? You will see that we have 0.25 or 0.5 or 1 or 2. If the structure is surrounded by taller structures or trees, taller structure or taller trees within a distance of 3h or 3 the height of the structure itself, then C1 will be 0.25. And you will see that if we go down, if it is an isolated structure on a hilltop, then we will use a C1 as 2. So this representing the probability of hitting the lightning to our structure. So you see here that this one is 0.25. This one have a low probability or low value. Why? Because we have taller structures around our building. So the lightning will definitely hit the other ones with higher probability. Okay, so the other structures will have a higher probability that they will take the lightning. Okay, but however here we have our isolated structure on a hilltop. It is on a hilltop and isolated, nothing around it. So what does this mean? This means that it will have a very high probability that it will take the lightning. Okay, or it will be hit by a lightning strike. You can see that there is a values between them. If our structure surrounded by structures equal or less height than as our structure within a distance of a 3h, then we'll use 0.5. If it is isolated with no structures located with a distance of a 3h, then we'll use 1. So according to your own building and its location, you can select each of these values. So now we understand C1. The collective area is simply, here we have our building, we have a length, width and height of the building. The collective area is simply equal to the length multiplied by the width plus 6h L plus W plus 9 by h square. So by substituting with the length, width and height, we will get the collective area for our building. So now we have the collective area, we have C1. The only thing remaining is the NG, or the average flash density. Now the NG or average flash density in the region per year or strike per kilometer square per year can be obtained from this map. You can see it is from 0.1 to 70. The last value is 70. So for example, if you are here in the green one, in this region, then you are in this value, which for example can be from 2 to 4. Okay, from 2 to 4. If you are, for example, in this yellow one, for example, or the orange one, okay, orange but not very deep orange, okay, this one is like this one. So we can say from 10 to 20. We can choose a value between it according to how thick this color. Okay, so by knowing your location from this map, you can get the energy from here. As an example, 6, 2, or 10, or 30, or whatever the value you are going to choose. Okay, so let's get back. Now we have energy, we have AE, we have C1, and we get all of this, multiply all of this to get the ND, or expected lightning frequency calculation, or how many lightning will hit our building per year, the expected number. Okay, now the second one, which is NC, or the tolerable lightning strike frequency to the structure calculation. So NC, or the allowable number of lightning strikes, is equal to 1.5 multiplied by 10 to the power negative 3 over C2, C3, C4, and C5. Now, the only unknown here is C2, C3, C4, and C5. So now, C2, which is called the construction coefficient, depending on the construction of our building. So if we have a structure material, the material of our structure is a metal, non-metallic, or combustible. Okay, so if the roof material metal, non-metallic, or combustible, okay, any of these values according to the roof material and structure material, if it is a metal and the metal, we will choose C2 as a 0.5. Okay, if it is a non-metallic, we will choose 1. If it is metal and non-metallic, we will choose 1. So the more this value, the higher this value, means the C2 higher means lower allowable number of strikes. Okay, so lower values, higher values means lower allowable lightning strikes. Now for the third coefficient, which is C3, the structure contents coefficient, you will see that C3, depending on the structure contents, if it can change from 0.5 to 4, depending on the value of the contents inside our building. If it is a low value and non-combustible, then in this case we will choose 0.5. If it is, for example, exceptional value, irrepressible culture items, in this case we will choose 4. If we have a lower value, such as flammable liquids, computer or electronics, lower value than the culture items, of course. This one, like museums. Okay, number 4, like museums. The contents inside the museums are very important, so we have to protect them really great. So we will choose a highest one, which is 4. 4 high value means lower allowable number of strikes. Okay, and you will see between them different values depending on the content importance, or the value of the contents inside the structure itself. Okay, so we have C2, C3, we need C4 and C5. C4 depends on the occupancy of the structure itself. Is it unoccupied, or normally occupied, or difficult to evacuate, or risk of panic in this building? If it has a risk of panel, high occupancy, this means that we will choose the 3 value, or the highest value, which means lower allowable number of strikes. If it is unoccupied, then we will choose 0.5. Okay, C5, the lightning consequence. If the lightning consequence, the effect of the lightning on the environment, okay, and the facility, of course. Number 1, if it is we will choose 1, low value, in case of the continuity of the facility service is not required or not important. The building itself, the continuity of the surface inside the building itself is not important and does not have any environmental impact. However, if the facility surface is important or required, then we'll choose 5. If it has consequences to the environment, then of course we'll choose the highest one, which is 10. Okay, so we have C2, C3, C4, C5, and now we can get the value of NC. So we have the value of ND and NC. ND, which is the expected number of lightning strikes. NC is the allowable number of strikes. So if the expected greater than the allowable, then we need a lightning protection system. If it is less than or equal, then the lightning protection system is optional. Okay, now what is the next step? Now we understand if we need a lightning protection system, what we are going to do, the risk assessment calculation. We are going to get the lightning protection efficiency, which is equal to 1 minus NC over ND. So what is NC and what's ND? We discussed that NC is the allowable number of strikes. ND is the expected number of strikes. Now by calculating this efficiency, we will be able to choose the lightning protection class. Is it the first class, second class, 3 or 4? So if the efficiency required 98%, then we need the first one, which is the highest protection level. If it is, for example, 88%, then we will choose the third here, not second. We have another one, which is third, should be third here. And here should be fourth. Okay. Now, for example, if we have a value between them, as an example, 96. 96 means that we are between them. Then we will choose the higher value, which is the next level, which is the 98. Okay, to the next higher value. So now by knowing the lightning protection class, we are going to be able to design the air termination system. But first you will see that here we have applications according to the protection level. So for example, if we have the highest protection level, this is in the military applications, nuclear power stations, which of course have a disaster effect on the environment. Computer centers, of course, very important. Then we will choose the first lightning protection class. Photovoltaics, choose the third, and etc. Okay, you can see here different applications with their equivalent lightning protection class. Now we now did the risk assessment calculation in order to get the lightning protection class, the first, second, third or fourth. Now the next step is that we need to design the air termination system. We have 3 methods in order to do the air termination method. Number 1, by using a conventional Franklin rod. It means that we are going to use one rod in order to protect a certain area against the lightning strikes. Okay, so we use only one rod. So this type of lightning protectors were made up of a typically 6 meters copper rod. Okay, the height of the rod itself is 6 meters. And the protection radius is up to 30 meter in radius. The protection zone have a radius of 30 meters. It is used for protecting small structure areas or zones such as households, water tanks, watch towers and gardens. So this will be used in small applications, okay? But in important applications such as a big structure or a building, then we don't use the conventional type. We use 2 methods. Number 1, the vertical air termination rod method, or having a group of rods, as you see here, each of this rod having its own protection zone. Okay, remember here, this one rod having a radius which protects it, or a circle which protects it with a certain radii. Okay, now this one here, we will choose a group of rods. Okay, each rod forming a protection zone in the form of a cone. Okay, you see that here, this cone, this is our rod, and this is the area which protects it in the form of rod. Okay, and this area have a certain radius of the protected area, and also have an angle called the protective angle. Okay, so the area protected by this rod having a certain protection angle or a certain radius of protected area. Okay, you can see here that this rod protects this area and this rod protects this area. By knowing this radius plus this radius, we will know the distance required between two rods. Okay, so what we need to design is that we need to know the number of rods, and how to know the number of rods by knowing the height of the rod. We select a certain height, and according to this height we will have a certain protective angle and a certain radius. So you can see here that in order to get the distance between two rods, we will use this equation. Equation says 2 root 2RH minus h to the power 2. H is the height of the rod. R is the rolling sphere radius. Okay, remember that the rolling sphere radius is not this radius. Okay, this radius is called the radius of the protected area, not the rolling sphere radius. We will understand now what is the meaning of rolling sphere radius. So the height of the rod, okay, we'll see that this graph representing the protection angle, we can select any protection angle we would like, and the equivalent height. And you can see there is a curves, each of them representing the protection class. As an example, if we choose the first class, then we will have a height from 20 meters to 2 meters. This is the minimum height, from 2 to 20. Now, for example, if we choose a 10 height for the rod, then go up, you will find here a nearly 43 degree, for example. Okay, so this angle is a protection angle equivalent to the 10 meter height. Okay, so now we can choose any height we would like according to this graph. For example, the second one is from 30 to 2 meters. The third protection level is from 45 to 2 meters, and so on. So we have our H. Now the only thing remaining is the rolling sphere radius. Rolling sphere is obtained from the lightning protection level or the lightning protection class. If we are using the first class, then we will have a small radius of the sphere, 20 meters. If we choose a second one, we have a 30. If we choose a third one, 45. Fourth, 60, and etc. So we, from this table, for example, if we need the first level, then choose 20 meters as the radius of the rolling sphere. And what height? Get what height you would like from 20 to 2. Okay, as you would like. According to the height, you will know the distance between two rods. Okay, so now you know the building, you know the roof length multiplied by the width. Okay, so you will know according to the distance between two rods, you will know the number of rods required. Okay, now you will ask me, what is the meaning of the rolling sphere? This is an important question and very interesting theorem, okay, or theory. So let's go and see it. Now, the question is, what is the meaning of the rolling sphere? Okay, this is a YouTube channel or a video which I found in a YouTube channel called the Scientific Lightning Solutions. I don't know if this is a company or what, but anyway, they provide an animation for the rolling sphere. Okay, so what does this mean? The rolling sphere, okay, representing the movement of this pole. Okay, for example, according to our protection level, is it a first, second, third, or fourth? for example at 20 meters or 45 or whatever, this representing a radius of a sphere. Okay, so what you will see that here this sphere as if it is moving on the roof of the building. Okay, and the points it touching the building representing the possible location at which the lightning will strike our building. Okay, so you'll see that this is a ball moving, the points at which it touches our building representing the possible location of the lightning strikes. Okay, so you can see here this is a possible location, this one is a possible, this one is a possible. So we need to protect all of this area. How? By putting a rod, and this rod will have a certain protection region. Then we are going to put another rod with a certain protection region to protect all of this equivalent or red points in which our system or in which our lightning will strike the building. Okay, so you can notice that the larger the pole, larger pole means lower points at which it will hit the building, but a smaller one or smaller number of sphere or the sphere radius means more points are going to hit the building. You can see here that we put rods at the possible points at which the lightning will hit. Okay, you can see here that this pole representing the lightning hitting our building. So we need to protect all of this point. So this theory is called the rolling sphere. Okay, now let's get back to our slides. So now by knowing the height which we selected, we will know the protection angle and we will know the distance required between two rods. This one was the first method of air termination design. Second method is called the mesh method. Okay, mesh method is used for protection of the plan or flat roof structures. Okay, flat only. Okay, should not be used on curved surfaces. Okay, so how does the mesh help us? You will see that here this is a mesh. Okay, this is square, this is another mesh, another mesh. This mesh will have a certain area. This area depends on the class of the protection which we get. If it is a protection level number 1, then we will use a 5 multiplied by 5. Okay, or 10 multiplied by 10 in case of class 2, 15 multiplied by 15 class 3, 20 multiplied by 20 class 4. Okay, and you will find again the equivalent rolling sphere radius. Okay, a smaller rolling sphere means that we have a higher probability of more points hitting the building, or more points at which the lightning strike will hit our building. You can see here another one. This is also a mesh, and each of them have a protection zone which protects our building. So this is the third method, okay, not the second method. First method was the conventional rod. Second method is using the vertical rods. Third method is using the mesh method. Okay, here is another image, and you will see that all of these meshes having a down conductor going to the earthing system. Now let's go and see the down conductor. But before going to the down conductor, there is a fourth method, okay, which I forgot to mention. It's called the natural components methods. Now, according to the class of the lightning protection system, for example, from 1 to 4, in this case, if we have the material of the building itself or the structure itself, lead, steel, titanium, copper, and etc., and you will see here the thickness itself. Okay, for each of them we should have a certain thickness in order to use the natural components of the building itself, the metallic structure for the building itself, to be used in order to use it as a lightning termination system or air termination system. And instead of using rods or mesh or whatever, we can use the natural components inside the building, or on the roof of the building, such as metallic structure or pipes, in order to capture the lightning strikes and go down to the earthing system. So you can see that we have thickness T number 1 and then T number 2. If it is, for example, steel, then we need 4 millimeter and 0.5 millimeter. What's the difference between them? Number 1 prevents the puncture or hotspot or ignition. Okay, and T dash only for metal sheets if it is not important to prevent puncture, hotspot or ignition problems. Okay, so see that this one has a smaller value than this one. Okay, you will find here minimum thickness of metal sheets or metal pipes in air termination system. Okay, this is another method used. Now the second one, which is the down conductor design. The down conductor, which takes the lightning from the mesh or the rods or whatever and goes down to the earthing system. Okay, so according to the protection level, you will find the distance between conductors. If it is, for example, a protection level number 1, then we will use a 10 meter as a distance between two conductors. If it is, for example, protection level 2, then we need 10 meters. Protection level 3, then we will need 15 meters. Protection 4, 20 meters. Now, as an example, if we have a mesh, okay, which is 5 multiplied by 5. Okay, so this one is 5 and this one is 5. Then the down conductor needed in protection level number 1, which is mesh 5 multiplied by 5, we will need a 10 meter distance. So we will choose this down conductor and this down conductor. Why? Because 5 meter plus 5 meter give us the distance 10 meters required from the table. Now the last element in the lightning protection system is the earth termination system. According to the earthing system, we need a certain earthing resistance or earth resistance for the light current from 0.5 to 1 ohm, low voltage 5 ohm, medium voltage to 0.5, high voltage 0.5. For the lightning protection, which we are doing now, we need a 10 ohm for the recommended earth resistance. Okay, so we understand now that we need an earthing system with a resistance of a 10 ohm. How to design it? We discussed it using ETAP and using manual calculations on our channel. So in this video, we discussed the lightning protection system. If you like this video, don't forget to hit the like button and don't forget to subscribe to our channel. Thank you.